Okay, so our next section, we're going to talk about basics of digital modes, packet, receiving, transmitting digital modes, digital operation, digital modes. It's going to be a lot of fun. All right. So some of the basics of a digital mode, where to find digital activity. So communications are digital modes if the information is exchanged as individual characters encoded as digital bits. Such as Morse code, radio teletype, PSK31, FT8, D-Star, DMR, slow scan TV. Those are all forms of digital modes. Digital modes are restricted to CW/data segments in the HF band. They're found near the top of the CW segment. On 20 meters, most PSK stations are near 14.070, RTTY other modes between 70 and 14.112. We've got a table coming up that shows some of that. CW isn't formally restricted anywhere in the bands. It's a digital mode, but you can use it anywhere. It has special privileges. Data rates and bandwidths are specified by the FCC rules. Digital codes not specified by the FCC must be public. Remember, you can have an experimental mode, but it's got to be published. People have to know what it is. Radio teletype originally used mechanical teleprinters, but migrated to computer sound cards. Most people use a computer sound card to generate their digital tones these days. PSK31, real popular. It's a good weak signal mode. Uses low transmit packet teletype over radio. WINMOR is Windows-based messaging over radio. WINMOR. All those are popular types of HF digital modes. And there's packet radio, common on VHF, UHF, 1200, 9600 baud on those bands. Okay, so here's the bands. Here's the frequency range of where you'll find some of the digital stuff hanging out. Most people adhere to that. People follow it pretty well. So here's some definitions that you might want to know for digital stuff. Air link, that's the part of the comm system that involves radio transmission and reception of signals. I don't think I've ever used that much, but that's air link. A bit is the fundamental unit of data, a 0 or a 1, representing all or part of a binary number. There's the bit rate. That's the number of digital bits per second sent from one system to another. Baud is a number of symbols per second, and symbols can be 10-bit or 8-bit based on the protocol you're using, but it's symbols per second sent from one station to another. The duty cycle is the ratio of the time that the transmitter is on to the total time plus the off time. Protocol are the rules that control the method used to exchange data between systems. And the mode is the combination of a protocol with a modulation method. Digital modes are regulated as voice emissions by the FCC, digital voice modes, and those include D-Star, System Fusion, AOR, digital voice system, and DMR. FSK, individual bits of data encoded as tones. FSK uses tones. As data are transmitted, different tone frequencies are used to represent the 1 or the 0. The frequencies in a two-tone FSK system called mark and space. Space represents a 0 and mark represents a 1. In direct FSK, the frequency of the transmitter's VFO is controlled by a digital data signal from the computer. So you either can send two tones through the audio passband, or you can actually change the carrier frequency. Same thing. It's a frequency shift. It's the same result. Audio frequency shift keying, which is probably 98% of what we do in the ham radio, is use audio tones modulated on single sideband or FM through the microphone input generated by a sound card, typically. Multiple FSK uses more than two tones and are used to create more codes. Most common type of the PSK, the phase shift keying. Most common type of phase shift is to invert one of the tone waveforms by shifting it 180 degrees. Rapid changes in phase can be heard from the human ear as a raspy noise or buzz. The signature of a PSK signal on the air received by CW or CW single sideband receivers sort of sound like an old computer modem. So let's talk about some questions here. In what segment of the 20-meter band are most digital modes operations commonly found? It's around between 14070 and 14100. D. What is a direct binary FSK modulated signal? Direct. Now we're doing direct, so you want to key the oscillator directly with the digital signal. It must be V. Okay. How are the two separate frequencies of a frequency shift keyed signal identified? Usually do mark in space. D. Which of the following provided digital voice modes? Okay, remember digital voice modes, DMR, D-Star, and Fusion. Those are digital voice modes. All these other ones have the non-voice modes. Okay, let's talk about some character-based modes. Simplest use of digital communications is a mode in which individual characters entered by an operator, then transmitted to another station, and they appear on read by another operator, such as Morse code. Speeds are low but convenient to use and require a little additional equipment than a sound card or a modem. So a lot of times it's keyboard to keyboard. I type the letter A, I transmit it, the receive station gets it, puts on his computer A. So we just did some character-based transmission. Sometimes referred to as keyboard to keyboard or chat. You transmit a stream of characters without additional data. That's referred to as unstructured. Oldest form of ham radio digital communication is RTTY. This is called Baudot. It's a timing sequence for the bit pattern. Here we're trying to send the letter D as in dog. The starts bit is set. You have some bits that tell it when it's starting, then the data comes across, and then you get a stop bit, and you're done. And how fast it goes out is a baud rate. Okay. RTTY uses the Baudot code, which represents each character as a 5-bit sequence. 5-bit allows for 32 different characters. That's not enough for the entire English language, numerals and punctuation. There's 2 special flags, letters and figs, that are used to switch between the 2 character sets. And that doubles the amount of characters that can be sent. So there's a special character. There's a guy sending letters or numbers or something. You can set it, and you get, you don't increase your 5 bits. Don't have to get bigger. Difference between mark and space tones is called the signal shift. RTTY, usually that's at 170 hertz. It's the most common. It's not a rule, but that's what just about everybody uses. PSK31 is another mode. It's probably the most popular phase shift key mode. It's called 31 baud by some people. Uses a sound card to generate the RTTY signals. 31 is the symbol rate. It's actually 31.25 baud. Designed for keyboard to keyboard communication. Typing at rates up to 50 words per minute. So that's fast enough for me because I couldn't type that fast. And as referred to as BPSK31, QPSK sends 2 audio tones. So there are now 4 possible phase combinations. Okay. So since PSK has 2 tones, you have to select the right sideband, the correct sideband here, either upper or lower. If you're in the wrong sideband, you're going to invert your tone, so you're not going to decode it. So make sure you understand what band you're on. Usually it's upper sideband, even no matter what band you're on for the digital modes. But if you're tuned in and you're not copying, swap sidebands and see if it starts reading correctly. So it is sideband sensitive. PSK uses a variable length character called Vericode that assigns shorter codes to common characters and longer codes for uncommon characters, like Morse code. Capital letters and punctuation take longer to send. If you're used to RTTY with no lowercase, turn off caps lock because they take more. Something I didn't know for a while was I didn't know it was any different on the character you sent, whether it sent 8 characters or 3 was based on what you had typed in there. So really, I typed so slow it didn't make any difference, but that's an interesting fact there. So QPSK31 and PSK31 have about the same bandwidth, 2.5 kilohertz. QPSK is sideband sensitive and its encoding provides error detection. So what is the most common frequency shift emission on the amateur HF bands on the shift? 170 hertz, number B, letter B. Which of the following is characteristic of QPSK? Coding error correction is about approximately the same. Sideband sensitive, I think all those sound right. That's correct. Which of the following describes Baudot code? It's a 5-bit code. That'd be C. Which of the following statements is true about PSK31? Application will use Vericode. Yep. B. Would be B. Which type of code is used for sending characters in a PSK31 signal? Vericode, A. All right, talk about some packet-based. These are structured modes, and they're derived from early teletype over radio or computer-to-computer network systems. Hams have adapted these protocols, creating packet radio, PACTOR, WINMOR, and other communication systems. Some packet modes, JT65 and FT8, require precisely defined transmission periods. The utility software is available to keep your computer synchronized within 1 second of the standard time. So some of these modes, like FT8, JT65, your local time source is important to have it synced within a second of the guy you're talking to. So some of the basics of packet. Packet refers to the transmission of data in structured groups called frames. Packet communication systems package the data with control and routing information and add error detection information. Each package of header data and trailer is called a frame. Different packet protocols are used for different sets of information and methods of creating the frame, but basically the same. You usually have a header, you have the data, and you have some kind of trailer. The header contains the bit patterns that allow receivers to sync with the packet structure, control and routing information, and for some protocols, error detection correction. The data is the data to be exchanged between the systems, usually ASCII characters, usually compressed for efficiency. The trailer then is added on the information at the end for error detection. Forward error correction goes beyond simply detecting errors by including redundant encoded info with the data. It's possible for a receiver to correct certain types of data errors. Most common error detection mechanism is called a cyclic redundancy check, or CRC. On an ARQ system, automatic repeat request, if mismatch is detected, the receiving system responds with a NAC, which not acknowledged, and the protocol requests retransmission. The transmitting system will continue to send packet until it's received without error or retransmissions has reached a limit. Okay. ARQ is used in PACTOR, packet radio, and WINMOR. ARQ protocols were used for wired network connections, and the transmission can only be received from one receiving station during the connection. This means you can't break into a contact between two stations using ARQ. So if Jason and I are talking ARQ, our systems are trying to talk to each other. If somebody else gets in there, we're not going to respond to them because we're trying to complete our handshake. So that's what they're talking about here. You can't break in. If two stations are talking, don't try to break into them because you're not going to be acknowledged and you're just going to cause interference on what they're trying to do. So that a station can advertise its presence, however, ARQ protocols provide a broadcast mode to transmit without another station having to establish contact. So you can there's a mode we use like calling CQ in ARQ, and if somebody hears it, their station will respond, and the two of you will pair up. I used to do this long time ago. What's the AppCore? I forgot what it's called. Long time ago. A MON mode is also provided so that stations can listen to the other stations without getting into their error correction scheme, right? Using the MON mode allows you to determine if the frequency is occupied by two stations having an ARQ mode contact. It's designed to transfer data between only two stations, meaning that you can't break in onto the contact. Talked about that. Packet radio, TOR system developed to compensate for transmission errors in RTTY, used almost exclusively on the UHF bands. Packet radios send short bursts of characters with error detection and correction data. It's based on computer network protocols X.25, one of the oldest packet switching communications protocols. Popular during the late 1970s and 80s, back when I was learning about stuff. That was slick stuff back in the day. Packets exchanged using VHF FM voice at 1200 and 9600 baud. Today we've got some improvements over that. It does not work well with HF broadcast because of the noise and fading. And HF, you'd have to be at 300 baud or lower. The HF UHF packet still big around here. Works good. Okay, PACTOR and WINMOR. So these reliably, I mean, they're reliable. They're kind of slow, but they're reliable and they're robust. PACTOR is packet-based TOR. WINMOR is WIN-based TOR. They work pretty well. PACTOR 1 uses frequency shift keying, modulation. PACTOR 1 through 4 use advanced PSK. PACTOR 4, not yet legal for U.S. amateurs. Might be coming close. I mean, there's legislation. They're working on getting that, but it's a very good mode. They work fine. PACTOR and VARA modes have overcome some of the issues with HF. I know we use VARA on our packet system here. We do dual mode packet or the regular packet 1200 baud. VARA works well and seems to be doing good around here. Okay, Winlink. So Winlink is a way to transfer email or messaging over HF. We use it VHF, UHF here also for our Aries work, and it's a well-established group. We've got several Winlink ports here in town, and they work very well. And Winlink isn't a mode; it's a gateway communication system. It uses the internet to connect its email services with a gateway and mailbox stations around the world on HF, VHF, and UHF. Said it's been around a while. It's been improved a lot, and it's fairly reliable. And when all else fails, it's a good mode to get stuff going. Winlink stations do not connect directly to the internet, but they provide a means for stations out of your local internet coverage to connect in range. So that's pretty cool. If you have a regional outage somewhere, power, data, fiber optic cables cut, no internet, it allows you to connect RF to somewhere place else that does have internet connection. You can get your email and your data through. So even without internet connectivity, Winlink Express, which is a program you can download, runs on your PC, can act as a standalone mailbox station or communicate directly with each other. You can do peer-to-peer connections, done all that. So on HF, Winlink uses PACTOR and VARA modes. VARA is the most popular, is the more popular. VARA is a TOR software developed by EA5 HVK software. So check that out. Okay, FT8 and WSPR. These are called weak signal modes. They're supported by the WSJT software suite. A lot of cool modes in there. You can go check it out. They use 8-tone frequency shift keying modulation and error decoding correction to enable successful decoding at very low signal to noise ratios. FT8 sends 75-bit messages, limits messages to call signs, grid locations, and signal reports only. FT8 signal reports are on the signal to noise ratio, so a report of +3 means the signal is 3 dB above the noise floor. Most common FT8 transmission ranges are in 14.074 to 14.077. Be sure to locate a clear frequency and select the time slot that doesn't interfere with the calling station. Specifically, when responding, select a clear frequency in the alternate time slot, so that used by the calling station. So FT8 is very popular. Done a lot of that myself. It's a lot of fun. WSPR, it's an HF propagation path for weak signal things. I run 2 WSPR nodes from my home on 30 and 20 meters all the time. It doesn't support two-way QSOs, but I have a beacon that transmits and all the time, and I can go look at signal reports and see who's seen my signal around the country. It's fun. Built the whisper nodes myself, fairly easy to do, and it's fun to play with. Okay, low power whisper transmitters generate coded packets. Stations that receive these reports can report them on the whispernet.org, and it's fun to go look at your signal reports and see what you can see. So, okay, amateur wireless networks. Certain wireless networks, when networking frequencies overlap with amateur bands, amateurs are able to use them for many of the same purposes that unlicensed users are able to, such as text messages, voice over IP, email, etc. If you operate a wireless network on FCC Part 97 frequencies, you must comply with the prohibitions on encryption. Ham use two basic network topologies, mesh and star configurations. An advantage of the mesh network topology is that if one node fails, the packet may be able to find its destination by routing through another available node. So here's some wireless network frequencies that we have that we can share and use. And in these bands, there are some ham specific channels that are on our side, which really makes it nice. Arden is an amateur radio emergency data network. It's a mesh network, can be made. It uses commercially available routers in the 900, 2.4, 2.4, 5.8 gigahertz band. Arden website, one of the best websites I've seen for information and how to understand and get information. They do a great job. There's go to the ardenmesh.org if you're interested in that. Generally used during emergencies to support communication events like road races, parades, and other large gatherings. But it uses, you can use the commercial items, put them into the ham bands, and they work. They work great. Let's see, it's a digital protocol used with Winlink. B. Which of the following is a good practice when using a transmitter frequency to answer a station calling CQ using FT8? I think you want to call, you want to find a clear frequency during the same time slot as the calling, and the alternate time slot as the calling station. So that would be D. Which of the following is required when using FT8? You need a computer with accurate time within 1 second. That's the key. B. How do you join a contact between two stations using the PACTOR protocol? Is not possible. C, because it's only limited to two stations. So C is it. What is the primary purpose of an amateur radio data network, mesh network? It's C, to provide high-speed data services during emergency or community event. Which of the following describes WinLink? It's a wireless network capable of both VHF and HF band operation, form of packet radio, and all of those. D. What is another name for a WinLink remote message server? It's called a gateway. Which of the following is a common location for FT8? It's between 14074 and 14077. C. What type of modulation is used by FT8? It uses 8-tone frequency shift key. A. What is QPSK modulation? It's modulation using, let's see, the angles, degrees, phase shifts at the bottom. D. Which digital mode is used as a low power beacon for assessing HF propagation? That would be a whisper node. Weak signal propagation. Yep, A. What part of packet radio frame contains the routing and handling information? That's the preamble. Oh, excuse me. Sorry, it's the header. The header has the information containing the routing and handling information. Sorry about that. The header. In an ARQ mode, what is meant by NAC response to a transmitted packet? It means, how does forward error correction allow the receiver to correct data errors? By transmitting redundant information. C. What does an FT8 signal report of 3 plus 3 mean? That means it's 3 times the noise level. Yep. All right. Most digital modes on HF are transmitted as USB signals. The exception is RTTY. It uses LSB. Modem and software must be configured for the correct baud rate, receiving tone, receive data, signal strength, to be tuned correctly. Since PSK uses a single tone, either USB or LSB will work. Most use USB. Like other amateur signals, digital mode bandwidth is defined by the FCC. The bandwidth of signal changes with symbol rate. As symbol rate increases, so does the bandwidth needed for the signal needed to transmit them. Most common method of transmitting these modes is to connect to an audio output of a computer sound card to the microphone of a single sideband transceiver. So most of the time you're going to use your computer to connect sound card connected to the radio. Here's a chart that shows some of the bandwidths of the different digital modes. What's interesting to point out here is like PSK31 and FT8, they're 50 hertz wide. We don't send a lot of information there, but they're 50 hertz wide. So that means you could put 50 QSOs, 50 times 5 is 2,500 in a, you need some spacing, but you could put a bunch in a audio passband, right? So sometimes you'll see in the FT8 modes, just the whole passband is loaded with signals. So you can get a lot of QSOs in one. It's very efficient, 25% of the time. But FM modes and these digital modes, you're transmitting full power the whole time that you're transmitting. And those times, those can be several seconds to half a minute or something. So you have to be real careful. Make sure you watch your transmitter. Don't exceed its average power rating. So reduce the transmit power to prevent overheating, usually by about 50% is usually a good idea. Digital modes can generate interference just like phone and CW. For digital modes that use a single sideband transmitter to transmit audio, FSK, most common problem is supplying too much or too little audio from the computer to the radio's microphone input. A waterfall display, the vertical lines represent spurious emissions caused by overmodulation of the transmitter. ALC and digital modes, automatic level control, they're used for preventing excessive drive to the amplifier inputs. The ALC circuit reduces gain when power level gets too high. However, it comes at a price. The signal compression can result in distortion. Resist temptation to turn up gain. For digital signals, distortion caused by ALC makes the signal harder to decode, creates spurious emissions. It's similar to overmodulation. When in digital mode, your ALC system should be either disabled or input level and gain turned down to the point where the ALC does not activate. So my experience operating FT8, or any of the digital modes, this is probably the most common error, mistake, misunderstood piece by some new operators. They don't have their ALC, their audio input adjusted right. You can turn it off, but what I do is I have mine turned on, but I have it right below where it cuts on, just like it says. So that seems to be the right sweet spot for me. But you can see a station when they're really overmodulating their signal. Their call sign will show up 4 times in the FT8 passband, right? So, so this is probably the most important thing to go adjust and correct is get your audio levels right coming from your from your PC. If you're using a Windows thing, Windows sometimes does favorite things to your sound card when you didn't want it to, an update or something. So always check this and make sure you got an eye on. I always have my my ALC meter up on my so I can always see if something's going on there. So ALC is a big deal in digital modes. All right, let's get into some practice questions. Which mode is normally used when sending RTTY signals? So RTTY is almost always done in lower sideband. And for all the other digital modes, it's usually upper sideband, which is B. What could be wrong if you cannot decode an RTTY or other FSK signal, even though it apparently tuned in properly? Mark and space can be reversed. Wrong baud rate, wrong side. I think all those sound correct to me. That is correct. What should the ALC system? Why should the ALC system be active when transmitting AFK signals? Too much ALC can cause a transmitter to. I think it's B. The ALC can distort the signal. Why is it important to know the duty cycle of the mode you're using when transmitting? You want to make sure you don't exceed your transmitter's average power rating, which would be B. What is the relationship between transmitted symbol rate and bandwidth? The higher symbol rates require wider bandwidth, so that's B. What is indicated on a waterfall display by one or more vertical lines on either side of the data mode on an RTTY signal? Usually that's overmodulation, D. Okay, let's talk about in a digital mode, how do we initiate a contact, right? So like voice mode, you type in CQ, this is, my case, KM4CJ, say it a few times, put a K at the end, saying, hey, I'm waiting for someone to contact me, that I'm over. And then the response station would say, my call sign, this is, followed by the answering station's call sign with the K at the end. Modes such as PACTOR and WINMOR, the software modem will have a specific disconnect message. But notice the K here, it's used at the end of a transmission to indicate the other station is to transmit as shown. So that says that I'm finished waiting on you, right? It's like over. If you connect to a gateway, the exact way you connect to the gateway depends on the equipment and the mode that you're using, but usually begins with some kind of a connect message. If the signal is received without error, there's usually a handshaking, or they call it training sequence of packets to help for the two stations to determine the right the baud and the protocol to use. Because these stations respond without a human control operator, they are operated. A lot of them are automatically run, so they have to fall under the rules of the automatically digitally controlled station rules, which restricts them to certain parts of the band. And stations under FCC rules must operate under local remote control with control operator in charge of all transmissions. That's the rule. Here's where you can find on the band plan, these automatically controlled digital stations are allowed to operate here. Okay. During the console, a waterfall is kind of a neat display. It shows all the nearby signals. This is a PSK31, looks like the waterfall. It displays a series. It shows the presence of signals in a series of lines representing the scan across the frequency range. Signal strength is represented by brightness or intensity or color. As new lines are captured, older lines are removed. As it moves down slides down the screen, it's called the waterfall. Tuning age for an RTTY signal. If I've got looking at an RTTY signal on a spectrum analyzer or my audio spectrum analyzer, the vertical lines are the mark and the space. Those are these lines right here. And help tune in. So you would tune across the band. You want to line up your, as you move this wiggly line across, you want to line them up to these right here. And helps you tune in the signal. There's also, you can look on a oscilloscope kind of a thing and see the crossed ellipse on the right. They're used to see how well fine-tuned. If you're perfectly tuned, you'll see two ellipses perfectly at 90 degrees angles. That indicates how good your tuning's going. That's a pretty good looking signal there. Okay, third-party traffic. All the rules about third-party traffic apply to digital transmissions. You know, that includes the information in the emails, the digital messages. If you transmitted a web page or whatever kind of thing, third-party rules still apply. Commercial messages may not be transmitted via amateur radio. So, interfering signals in digital modes. Hidden transmitters. If I'm talking to a guy over in Europe, FT8, I only hear him, but over in Europe, he may be hearing 3 or 4 guys on the same frequency I'm on, but I can't hear them. So I may have a hard time talking to him. So that's sort of what we refer to as he's hidden to me. Okay. The result is unintentional, but it prevents us from completing the contact. On packet modes, PACTOR or WINMOR, they don't recover well from noisy and weak signal, weak environments. So you get a lot of failure. If you get a lot of failure to connect or frequent retries after a long time, it may just be band conditions are too noisy. Try a different band or something like that. So here's some practice questions for this section. What's required to conduct communications with the digital station operating automatic control outside the automatic control band segments? It's going to be A, the station initiating the contact must be under local or remote control. Same rules that apply for voice, for controlling the station with automatic control. On what bands may automatically controlled stations transmit RTTY or data emissions communicate with other controlled stations? I think only on the band segment where it's permitted. Anywhere in the 6 meter or shorter wavelength bands or limited segments. That is correct. It's specifically on the 6 meter band on this particular one. These are automatically controlled stations transmitting RTTY. You know, two of them. There's only one place you can do it. That's the 6 meter band. What symptoms may result from the other signals interfering with the PACTOR or VARA transmission? What symptoms? Frequent retries, long pauses, failure to establish connection between the station, all those symptoms that we've got interfering signals. Okay, which of the following is a way to establish contact with the digital messaging gateway system? You don't send an email to the control operator. Transmit it's a connect message is how you try to connect to them. That'd be D. What action results from a failure to exchange information due to excessive transmission attempts when using an ARQ mode? I think connection is dropped. That's correct. Because there's a timeout timer. You're going to try to talk to somebody. If you're talking to them and somehow you lose connection, there's a number of retries and then it gives up. So that's B. Which of the following describes a waterfall display? Let's see. Frequency is vertical. Amplitude is horizontal. Signal strength. Let's see. Signal strength in time. It would be C. Frequency is horizontal. Signal strength intensity is all vertical. Right? And that's the end of this chapter. So you want to do another module? You want to stop for today?
It's kind of loud in here.
Yeah, I think it is loud for those guys. That sounds good.
I'm good with that.
Okay. So
Was that the end of 8?
that was okay. Our next topic we're going to talk about is here is dipoles, ground planes, and Yagi antennas. The most fundamental antenna we have in amateur radio is a dipole. It's a straight conductor that's half wavelength long with the feed point in the middle. It's also known as a doublet antenna. The strongest radiation direction of the dipole is broadside to its axis in a plane containing the antenna's conductor. The weakest radiation is off the ends. The shape of azimuth pattern for a dipole in free space is shown in the next figure, and I'll show you. Here's a picture. This is what it looks like. Again, you've got a half wavelength piece of wire, feeding it in the center, stretched out horizontally, and this is the radiation pattern. So you can see it has radiation pattern broadside and to the back, with less radiation to the sides. So very fundamental antenna, great antenna, probably the most popular type of antenna we have using in the HF bands. Okay. Dipole is often used as a reference antenna for gain measurements. Gain is measured in dBd. Isotropic antenna is a reference antenna with a gain given in dBi. The isotropic antenna is a theoretical antenna. It's an antenna that radiates equally in all directions. So sometimes you'll see an antenna, the performance reference to dBi or just dB with the gain. So there's a way to convert between the two. To convert from dBd, which is dB dipole, to dBi, which is isotropic, is you add 2.15 dB. To convert dBi to dBd, you would subtract 2.15 dB. Current in a half-wave dipole is highest in the middle, that is in zero at the ends. Voltage along the dipole is highest at the ends and lowest in the middle. So if you have a dipole antenna, just remember that the current is the highest in the middle, voltage is in lowest in the ends, and the voltage is the opposite. the half-wave dipole, as we see here in this figure, has its maximum current at the middle, and the maximum, has a maximum current in the middle and maximum voltage at the end. The feed point impedance is lowest in the middle. The odd harmonics of the fundamental frequency of the dipole feed point impedance is low at the midpoint, once again, as shown. So if you've got harmonics, this is what they would look like based on if it's second, third, fourth harmonic. Again, the impedance is lowest in the middle for this dipole, and typically dipoles about 68, 62 ohms. Okay. The impedance increases as the feed point is moved away from the center, several thousand ohms at the end. Popular antennas are in-fed half-wave, off-center fed half-wave. You'll hear a lot of those. Those are different variations of where you feed the antenna. The in-fed, as an example, is popular for portable operation. It's lightweight, easy to install. It's a half-wave dipole fed at one end. In free space, the half wavelength is equal to about 492 divided by the frequency in megahertz. This is if you want to get the length in feet. You'll generally find that the length will be shorter than the free space wavelength calculation. However, for these exam questions, you don't have to take that into account. Just be aware that wire thickness and height above ground influence the resonant length. And the length again in feet, 492 divided by the frequency and wavelength. So what is the approximate length of in feet of a half-wave dipole resonant at 3.55 megahertz? How would you calculate that? Well, remember we take our 492 divided by 3.55 and you get 139 feet. So that would be the wavelength, 40 meters on 80 meters. Remember, the actual antenna will be a little shorter than this, but build to that calculation and use your tuner to tell if it needs trimming. Ideally, you want SWR as close to 1-to-1 as you can without tuning. So what's the approximate length in feet of a half-wave dipole at 14.25 megahertz? This would be 20 meters. So remember to use your formula, 492 divided by 14.25, and you get 34.5 feet. Okay. Center-fed dipoles are the easiest to use on the band, which they are resonant. The feed point impedance is a good match for a 50 or 75 ohm coax, and for coax on odd multiples of the fundamental frequency. A dipole doesn't need to be straight to be effective. Dipole can be supported in the center, where the feed line can be conveniently attached. There's another configuration called an inverted V, where you take the ends and lower them down. As long as the legs of the dipole form an angle of 90 degrees or more, the inverted V is nearly as effectively as a horizontal installed dipole. So how you fix your dipole, or how you, based on the area that you've got or the place you have to mount your antenna, is going to determine a lot what's going to be the shape of your dipole. But don't worry too much about trying to keep it perfectly horizontally, or get your antenna up, tune it, get on the air. The ground plane antenna is one half of a dipole, with the missing portion made up by an electrical mirror, or so we call that the ground plane. It's made from sheet metal or screen of the radials can be, the ground plane can be made from sheet metal or a screen of radial wires. Basic ground plane is a quarter wavelength long, with the feed point at the junction of the antenna and the ground plane. For HF ground plane antennas at ground level, radial wires are laid on the surface of the ground, or they can be buried within a few inches of the surface. Ground planes are called verticals because that's usually the way usually the way they're constructed and how you install them. A ground plane radiates best broadside to its axis. If installed vertically, the ground plane antenna pattern is omnidirectional. That is, it's uniform in all azimuth angles or directions. Very useful for VHF and UHF mobile portable communications, where the signals may come from any direction. Here's a picture of a ground plane. Again, you've taken that dipole and you've made it a quarter wavelength tall, and you've taken the other half of the dipole, you've made that your ground plane now. So the ground plane, whether made of solid metal or radial wires, creates an electrical mirror that image of the quarter wave antenna. This creates the electrical equivalent of a dipole antenna. The feed point impedance at the base of an ideal ground plane is about 35 ohms, half of a complete dipole's impedance, because only half of the antenna is physically there and able to radiate the energy. So remember, the dipole, center fed dipole, is about 60 to 63 ohms. The feed point impedance of a ground plane antenna with radials perpendicular to the antenna, approximately 35 ohms, resulting in a 1.4 to 1 SWR with a 50 ohm coax feed. Drooping or sloping the radials gradually raises the feed point impedance until the radials droop as so far as to become only one half of the dipole. The feed point impedance becomes 72 ohms. So a 50 ohm feed point is reached with radials drooping approximately 45 degrees. These are real popular for VHF, UHF. They're easy to make, and you just put your quarter wave, whatever, your 2 meters or 220 or 440, and then do your ground radials and bend them slightly 45 degrees, and they work great. You can put them in your in a closet in your attic, and they're great antennas. The droop angle, 30 to 45 degrees, was shown in the last figure, results in a feed point impedance approximating 50 ohms. As with the dipole, it's not useful to provide a one-size-fits-all formula for the length of a ground plane antenna. Since the ground plane is one half the size of a dipole, start with one half the free space length and be prepared to trim the antenna's length. So you always want to start longer than you need, because once you start trimming the antenna, sometimes it's difficult to go back the other way. So what's the approximate length in feet of a quarter wave monopole antenna cut for 28.5 megahertz? So remember, a quarter wave, you're going to use 246 divided by the frequency. So 246, it's a quarter wave. 246 divided by 28.5, 8.6 feet. So a 10 meter quarter wave vertical is about 8.5 feet. All right, mobile HF antennas, they're often some form of a ground plane. Most popular is the vertically oriented whip antenna for mobile operation. A full-size quarter wave mobile whip, though, is really not feasible on bands below 28, 24 megahertz. They're just too long. So you'll see what they call loading. There's some loading techniques that are used to increase the electrical length. Usually, sometimes you'll see loading coils, a coil added to the base or somewhere along the length. Sometimes you'll see what's called capacitive hats. They're spokes or look like a wheel-shaped structure added near the top of the antenna. And then there's linear loading, where part of the antenna is folded back on itself. So these techniques are all devised to load the antenna to make it think it's electrically longer than it really is. Another common feature of mobile whips is the corona ball at the tip. It does add a small amount of loading capacitance, but its main purpose is to eliminate high voltage discharge from the sharp tip of the antenna while transmitting. A loaded antenna is not as efficient as a full-size straight whip and will have a small operating bandwidth without retuning. When you add a loading coil to an antenna, puts a real high Q in that area of the band that you're operating in. So if you've got a large band, you may have to retune it as you move throughout the band, because, like I said, it's tuned it's got a very narrow high Q on it. The screwdriver antenna design, which is a whip with an adjustable coil at the base, changes the inductance. It has gained popularity for HF mobile operation. It is a good compromise between performance and convenience. And you may have seen them. There's a big coil at the base, and as you move between the bands, the coil moves up and down, changing the inductance. Pretty effective antenna. Great, like I said, great compromise antenna for HF mobile operations. So what's the effects of ground on these antennas? A dipole's feed point impedance and radiation pattern are both affected by its physical height above ground. The feed point impedance is affected because the electrical image is electrically reversed from the actual dipole. As the image and antenna get closer together, the actual antenna begins to be shorted out by the image. So below a quarter wavelength in height, dipole's feed point impedance steadily decreases until it's close to the ground level. It's going to be close to zero. So it's important to get the antenna at least usually half a wavelength up, if you can. Sometimes you can't do that, and I always say do the best you can. Try to meet the guidelines, but get something up, get on the air. That's the main thing. And this chart here shows the feed point impedance of a horizontal dipole over perfect ground, and you see it varies dramatically with the height. At ground level, down here in the bottom, it's shorted out. Basically, it's zero. As the antenna moves up gradually, it approaches about 72 ohms, about feed point impedance in free space. Above above 1/4 wavelength, the impedance varies as suggested in this figure over here, eventually reaching a stable value at a height of several wavelengths. So, so eventually as you get it higher and higher, it finally stabilizes up here. About 72 ohms is the feed point impedance when you get it real high. So 50 ohms feed point impedance, you can see here, is about 0.2 wavelengths above. So this chart just shows that the height above ground is going to change the feed point impedance. So you have to compensate for that. Height above ground also affects the radiation pattern because of reflection of the antenna's radiated energy by the ground. The direct and reflected signals take different amounts of time to travel to the receiving antenna, so they can add together, cancel each other, or any combination in between. So what happens when a dipole is raised in steps from a very low height to more than one wavelength above ground? And this figure shows some of those. These are four plots at different wavelength heights above ground. As a dipole starting at a 1/8 wavelength above ground is raised, the effects of its electrical ground image cause the elevation pattern to flatten out. At multiples of half wavelengths, the height pattern has a null in the inverted direction because the direct and reflected signals cancel. At heights below half wavelength, the dipole's pattern is almost omnidirectional and is maximum straight up. So the height above ground will change your radiation pattern of your dipole. There's another antenna called NVIS, which is near vertical incident skywave propagation. These are signals that go straight up. Signals radiated at high vertical angles on low frequencies are usually reflected back to the ground over a wide area, ensuring good communication. Horizontal dipoles from 1/10 to 1/4 wavelength high produce an omnidirectional high angle pattern ideal for the NVIS use. Like the previous chart showed, when that antenna got close to the ground, you saw the radiation pattern go more up in a round ball up towards the sky. So by lowering your antenna, you can change the effect of its radiation pattern and use it to bounce off the sky and talk regionally. It's used by many public service teams. Polarization also affects the amount of signal that is lost from the resistance of the ground. Radio waves reflected from the ground have lower loss when the polarization of the wave is parallel to the ground, that is horizontally polarized. Because the radiation pattern is made up of reflected waves combining with direct waves that are not reflected, lower reflection loss results in stronger maximum signal strength. So here's some antenna terms. Feed point impedance, that's the ratio of RF voltage to current at an antenna's feed point. Resonant, when an antenna feed point impedance is completely resistive with no reactance. We talked about that yesterday a little bit. Radiation pattern, graph of antenna signal strength in every direction or at every vertical angle. That's a radiation pattern. The azimuth pattern shows signal strength in the horizontal directions. Elevation pattern shows signal strength in the vertical direction. Lobes is the region in the radiation pattern where antenna is radiating a signal. Okay, that's the lobe. And then the nulls are the points at which radiation is at its minimum. Isotropic antenna radiates equally in all possible directions. Omnidirectional antenna radiates a signal equally in every horizontal direction. A directional antenna radiates preferentially in one or more directions. Gain is a concentrated transmitted or received signals in a specific direction. Front to back ratio is the ratio of gain in the preferred or forward direction to the opposite direction. And front to side ratio is the ratio of gain in the preferred or forward direction to directions at right angles. So those are some antenna terms that you will run into. If you look at an antenna spec, some of these things are spec'd out there, and some of these things, depending on what you're trying to do, these are important things that you'll need to consider if you choose the type of antenna that you want to use. Okay, what's the purpose of a capacitance hat on a mobile antenna? Do you remember that's the little ball that's up at the top of the vertical? Its primary thing is to increase the power handling capacity of a whip. Nope, that's not it. Reduce radiation resistance, to electrically lengthen or physically shorten the antenna, to lower the radiation angle, have to be C. But its primary purpose, remember too, is to static discharge. What is the purpose of the corona ball? That's the same thing on an HF mobile antenna, and that's to reduce RF voltage discharge from the tip of the antenna while transmitting, D. So what is one disadvantage of using a shortened mobile antenna as opposed to a full-size antenna? Let's see. That's the operating bandwidth may be very limited, right? Because usually you don't have a full-size antenna. You're gonna shorten it, and to make it tune, you usually put a coil in. That's going to really affect where you can operate in that particular band because it's a high Q circuit. Which of the following is a common way to adjust the feed point impedance of an elevated quarter wave ground plane vertical antenna to be approximately 50 ohms? So remember we talked about there, this is where you take those ground radials, we've got a vertical now, and if you bend them down just a little bit, bend them slightly downwards, that'll help raise the input, raise the impedance. So it's B. Which of the following best describes the radiation pattern of a quarter wave ground plane vertical antenna? So talking about a quarter wave ground plane, and it's omnidirectional. What is the radiation pattern of a dipole antenna in free space in a plane containing the conductor? Okay, so that would be, it's a figure 8 at right angles to the antenna. So you remember it's the radiating is broadside to the antenna, up, not broadside, but forward and back to the antenna. It's the antenna itself. How does antenna height affect the azimuthal radiation pattern of a horizontal dipole HF antenna at elevation angles higher than about 45 degrees? So this is, how does the height affect it? If the antenna is less than a half wavelength, remember that's sort of the key point high, the azimuthal pattern is almost omnidirectional. If you get lower than that, it starts flattening out. So C is the answer. Where should the radial wires of a ground-mounted vertical antenna system be placed? Let's see, on the surface or buried a few inches below the ground. So if you're doing a parks on the air, lay them on the surface of the ground. That works. That works great. If you've got a permanent installation at your house, you may want to bury them a little bit so you don't run over with the lawnmower. But don't bury them too low. How does the feed point impedance of a horizontal half-wave dipole antenna change as the antenna height is reduced to 1/10 of its wavelength above ground? Okay, so if you change the feed point is going to change, it's going to decrease as you change the height. When it comes closer to the ground, the feed point impedance is going to get lower. Eventually, get on the ground, it goes to 0. How does the feed point impedance of a half-wave dipole change as the feed point is moved from the center towards the ends? So the feed point impedance, you remember, of a center-fed dipole, around 60-something ohms. The more you move it out of the center and closer to the edge, it increases. So it'd be A. The impedance of an in-fed dipole is about 2,500 ohms. Off center fed, usually a quarter wave in, it's about 200, or it's at 2, it's about 200 ohms. So as you go from the center to the end, the feed point impedance increases. Which of the following is an advantage of a horizontally polarized as compared to vertically polarized antenna? You have lower ground losses. What is the approximate length of a half-wave dipole antenna cut for 14.25? So remember, it's 492 divided by 14.25. 20 meters is going to be about 33 feet. All right, there's the equation. 492 divided by 14.25. It's 34.5. So 34.5 with an answer, but you're gonna get the closest one, which is D3. What is the approximate wavelength of a half-wave dipole antenna cut for 3.55? It's going to be about 132 feet. All right, so remember, take 492 divided by the frequency for the half-wave length. That's going to be your answer. Okay, how about we got a quarter wave now? Remember, this isn't a half wave, so it's not 492, it's a quarter wave. So it's going to be 246 divided by the frequency. In this case, it's about 8 feet. So when they ask these questions, are they asking for the half wave, which is 492, or you get the quarter wave, which is half of that, 246. So keep that in mind when you see this question. Are they asking for the half wave or the quarter wave? Okay, how does antenna gain stated in dBi compare to the gain stated in dB for the same antenna? So the relationship is 2.15 dB, but is it higher or lower? And in this case, it's actually higher. How does an antenna gain? If you have a dBi antenna compared to a dBd, which is a dB dipole, it's 2.15 higher. Which of the following antenna types will be most effective as a near vertical incident skywave NVIS antenna for short skip communications on 40 meters during the day? Okay. Horizontal dipole placed 110 to 1/4 wavelength above ground, quarter to a half above. It's going to be a horizontal dipole, and it's going to be, remember, the closer you get to the ground, the more the radiation pattern is elevated up. So it should be A here, which it is. So less than a quarter wave to a tenth. Closer you get to the ground, the more radiation is going to be reflected up to the sky. Okay, what is the feed point impedance of an in-fed half-wave antenna? Let's see, in-fed is going to be 2,500 ohms, so we'd say very high, in this case, D. How does a screwdriver mobile antenna adjust its feed point impedance? It varies the loading with inductance. So you'll see a coil at the bottom and it moves up and down. That coil is an inductor, so it varies in the inductance, B. What is the common name of a dipole with a single central support? It's the inverted V configuration. Okay, let's talk about Yagi antennas. Directional antennas create gain as well as reject interference and noise from other than the desired direction. By aiming your antenna in the direction shown in the azimuthal projection map, you'll be beaming your signal directly at the other station. So as you point your antenna, that's the on a Yagi antenna, wherever you point it, that's the direction your energy is going. Dipole, ground plane, and random wire antennas use a single radiating element. But a dipole is an array antenna that uses 2 or more elements to create a maximum field strength in a specific direction. It's called the main lobe or major lobe of the radiation pattern. 2 types of arrays. There's the driven and parasitic. In a driven array, all the antenna elements are connected to the transmitter and are called driven elements. Parasitic array, 1 or more of the elements are not connected to the feed line, but influence the antenna's pattern by interacting with the radiated energy from the driven elements. Whether an array is driven or parasitic, its radiation pattern is determined by the constructive and destructive interference. If in phase, they will reinforce each other. If out of phase, they will cancel. Most popular of all directional antennas is the Yagi because of its simple construction and good performance. Yagi is a parasitic array with a single driven element and at least 1 parasitic element. The driven element is a resonant dipole, approximately half wavelength long. Parasitic elements placed in the direction of the maximum gain are called directors and are slightly shorter than the driven element. Parasitic elements in the direction of the minimum gain are called reflectors and are slightly longer than the driven element. The front to back ratio is the ratio of signal strength to the peak of the radiation pattern's major lobe, and that in exactly the opposite direction. So the front to back ratio is how much energy goes forward versus how much energy goes back. Okay, is a two-element Yagi shown in this picture here with a single parasitic element. You can see we've got a driven element here. That's your dipole. You've got a director. This is the direction of radiation. And you've got a reflector in the back. So this is the way the antenna is constructed, the way that it works. Yagi design trade-offs. Primary variables for Yagi antennas are the length and diameter of each element and their placement along the boom of the antenna. These affect the gain, SWR, front to back ratio in different ways. The more directors you have, this increases the gain. A longer boom with a fixed number of directors increases gain up to the maximum length beyond which gain is reduced. Larger diameter elements reduce SWR variation with frequency. Placing and tuning of elements affects gain and feed point impedance. So all those factors come into play when you're trying to design your antenna. There are other general rules of cause and effects, but these are typically on decision of the antenna designer himself. But when you go purchase Yagi and a Yagi antenna, someone has already figured out the size of the beam and the size of the directors and the parasitic elements, and you'll buy it based on front to back ratio and the gain that you need going and the gain that you are desired. Most Yagi designs have desirable radiation patterns, also have a feed point impedance somewhere below 50 ohms with regular coax. With the feed point impedance from 20 to 25 ohms, this results in an undesirable SWR of 2:1. So the most common technique for matching the impedance is a gamma match. A gamma match is a shortened section of parallel conductor transmission line that uses the driven element as one of its conductors. Transmission line transforms the low impedance of the feed point to a higher value. An adjustable capacitor, either an actual variable capacitor or a shorter piece of insulated wire inside a hollow gamma rod, is used to adjust the gamma match for an SWR of 1:1. A mechanical advantage of the gamma match over other techniques is that the driven element needs not to be insulated from the boom, which simplifies the construction. There's a beta match, which or sometimes referenced as a hairpin, is a short length or stub of parallel conductor transmission line connected directly across the driven element feed point. The stub acts as an inductive reactance that can compensate for any capacitive reactance at the feed point. The balun is used to maintain electrical balance between both halves of the driven element. Other techniques such as the omega match, impedance transformers, and transmission line stubs are also described, and you can read those in the ARRL handbook. Here's some practice questions. Which of the following describes an azimuthal projection map? Okay, map that shows the actual land masses wouldn't be that. It's going to be a map that shows the bearing distance for a specific location. Okay, so that when you're buying a Yagi antenna, remember it's going to project an azimuthal projection in the forward direction. Which of the following would increase the bandwidth of a Yagi and antenna? Larger diameter elements. The spacing will affect the gain and the impedance, but the element size actually helps with the bandwidth. Which is approximate length of the driven element of a Yagi antenna? That'd be a half wavelength. Remember, the driven element is the dipole, so it's half wavelength. How do the lengths of a 3-element Yagi reflector and director compare to that of the driven element? The reflector, let's see, the reflector is going to be longer, director is going to be shorter. Looks like it's going to be A here. Yeah, A is the answer. So the usually the director is right behind the driven element towards the back of the antenna. It's a little bit longer, and then in front of the driven element, what's the primary effect of increasing boom length and adding directors to the Yagi antenna? You're going to increase the gain. A. What does front to back ratio mean in reference to a Yagi antenna? It would be the power radiated in the major lobe compared to the opposite direction. Okay, so it's the ratio of how much power goes forward to the radiated power forward versus the radiated power in the back. What is meant by the main lobe of a directional antenna? It's the direction of which the maximum field strength from the antenna is radiated. So it's that direction. So the main lobe on a Yagi is usually on a Yagi is where the element is where the antenna is pointing out to the front of the antenna. Which of the following can be adjusted to optimize forward gain, front to back ratio, or SWR bandwidth of a Yagi antenna? Length of the boom, number of elements, spacing, all those things. D. What is a beta or hairpin match? It's a shorted transmission line stub placed at the feed point of a Yagi antenna to provide impedance matching. So it's a way to remember the Yagi itself is about 25 ohms. So you need something to raise the impedance up to about 50 ohms of your to your system. And the beta or hairpin match is a transmission line stub that does that transformation for you. Which of the following is a characteristic of using a gamma match with a Yagi antenna? Let's see. It does not require that the driven element be insulated from the boom. Our next section, we're going to talk about loop antennas, specialized antennas, and feed lines. So what's a loop antenna? It can be a circular, square, triangular, or any simple open shape that is not too narrow. Feed line can be attached at a break in the loop, or a small loop can be used to couple RF energy to the main loop. Square loop with each leg a quarter of a wavelength long is called a quad loop. A triangle or delta loops are usually symmetrical, each leg a third of a wavelength long. A one wavelength loop acts electrically like two dipoles connected end to end with the open ends brought together. Circumference much larger than one wavelength. Typically, current patterns around loop have more than two peaks and nulls. This results in an essentially omnidirectional pattern with the peak angle of radiation somewhat lower than a dipole at the same height. And there's quad and delta loop beams. Popular variation of the Yagi antenna uses what's called quad loops for elements. It's called a quad. It has two or more full-size loops mounted on a boom. Quad or delta loop beam-driven elements are approximately one wavelength in circumference and operate on the same principle of re-radiation and phase shift as does the Yagi. The driven element of a quad is about a quarter wavelength per side, and of a symmetrical delta loop, about a third of a wavelength per side. Quad and delta loops reflectors are about 5% longer in circumference than the driven element, and the directors about 5% shorter. Front to back ratio is generally better for the Yagi. It's usually better for the Yagi. That's right. Here's a figure here showing a wavelength of the loop antenna. So this is your antenna here, the square, and this is what the pattern looks like. The direction of maximum signal is broadside to the plane of the loop, whether round, quad, or delta, or orienting the loop vertically aims the maximum signal towards the horizon, which is good for DX. Full wave loop antenna. I've got a full wave loop antenna that I use, 160 meters. It's not up very high, so but it's the highest that I could get it, but 160 countries later, I think I'm pretty happy with it right now. So talk about small loops. When the circumference of the loop becomes less than a third of a wavelength, the current in the loop becomes relatively uniform all the way around the top, which causes so small loops cause radiation patterns to develop sharp nulls broadside to the plane of the loop. Small loops in wide use, they're in wide use as receiving antennas and portable or low profile transmitting antennas. The sharp null broadside to the loop makes them effective for direction finding. This is typically small loop. Now they have a very high Q. Sometimes they're difficult to tune. Some have an automatic tuner that comes with them, which is great. But they're very high Q. They're very high Q antennas. A halo antenna, which is double bent into a circle or square called the squalo, with the ends separated by a small gap. Not a continuous loop, but otherwise viewed as a half wave loop. Usually they're horizontally mounted horizontally, so they produce an omnidirectional pattern, with the horizontal pattern preferred for VHF weak signal operation. Halos for 6 and 2 meters can be mounted on a vehicle for mobile operation. So which direction is the maximum radiation from a VHF UHF halo antenna? And that would be omnidirectional in the plane of the halo. In which direction or direction does an electrically small loop, less than 1/10 of a wavelength in circumference, have nulls in its radiation pattern? And that's broadside to the loop. Let's talk about some random wire antennas. It's not practically always to have a half wave or a quarter wave long resonant antenna. A random wire can be used instead. Connected directly to the output of the transmitter or tuner without a feed line. This may result, however, you got to be careful. Random wire antennas may result in significant RF currents and voltages at the station equipment, RF burns. They can give excellent results on any band for which the transmitter or tuner can accept the feed point impedance. Typically, got to have a tuner with these because they're not resonant. You can stack antennas. Stacking antennas vertically or horizontally results in more gain. As more and more directors are added, the beam width of the main lobe, angle between points on the main lobe, which gain is 3 dB or less than maximum, narrows. Vertically stacking antennas increases gain and narrows the elevation bandwidth. Most vertical stacks with the antennas directly above each other are spaced about half of a wavelength apart. Spaced half wavelength, the additional gain for a vertical stack of 2 horizontally polarized beams is about 3 dB. You can double your power by adding another antenna on top. Here's an example of horizontally stacked and vertically stacked. So stacking the antennas produces more gain in the main lobe. 2 Yagis are stacked vertically at the same mass. So here's an example: vertical stack, horizontally stacked. Another antenna called the log periodic antenna. TV antennas are often log periodics. Log refers to logarithmic, and periodic means the spacing of the elements, which is referring to the spacing of the elements along the boom. The length and spacing of the elements increases logarithmically from one end to the other. It's designed to have a constant radiation pattern and low SWR over a wide frequency bandwidth, as much as 10:1, meaning the log periodic can be used over several bands. Not as much gain or front to back ratio as a Yagi antenna, but wideband, multiband, okay? And a log periodic antenna looks like this. The log periodic dipole array consists of dipoles fed by common feed line that alternates polarity between elements. Traditional TV antennas sweep the elements slightly forward. Beverage antennas was invented by Harold Beverage. They're designed not to have high gain, but to reject noise and interference signals that are not from the desired direction. It results in lower signal strength, but a better signal to noise ratio. It's referred to as a traveling wave antenna. It consists of a long, low wire, usually less than 20 feet high, aligned with the preferred signal direction. They're used exclusively for direction receiving on on MF and lower HF bands, 40 meters and longer wavelengths. It's high ground losses and it has high ground losses and is too inefficient for use as a transmitting antenna. But it's a great receive antenna, like I said, and it can improve your signal to noise ratio by rejecting some of the noise. Here's an example of the Beverage antenna. Usually 1 to 4 times wavelengths, usually kind of close to the ground. It has a terminating resistor. That's why it's not great for transmitting, because it's going to absorb all your energy. But it's a great receive antenna. And you can see by the pattern there, it's got great rejection to the back. Okay, so signals arriving from the direction of the terminating resistor, which is pointed towards the back, induce a traveling voltage wave along the wire. It gets transferred to the feed line and the feed point. Signals arriving from other directions are either broadside of the terminating resistor or do not induce voltage waves on the antenna. So a lot of people use these for a lot of your radios have a receive antenna, and this is one. This is an example of where you'd want to hook that kind of antenna in. Okay, talk about multiband antennas. What hams generally mean by multiband antenna is a design that reconfigures itself electrically for each band of operation. Most basic multiband antenna is a trap dipole. Each trap is a parallel LC circuit. A resonance acts like an open circuit. Below resonance like an inductor, and above like a capacitor. We went through that. We talked about LC circuits, tank circuits. At lower frequencies, the traps and inductance of the antenna make the antenna look electrically longer. And at higher frequency, the capacitive electrically shortens the antenna. Usually you'll see these on a beam antenna. It's got several traps, and these traps again make the antenna think it's 60 something feet long, and it's really only 25 feet long or something like that. So they're used quite a bit for beam antennas, for HF, because you practically couldn't put a big Yagi up at 40 meters. It'd be super long and heavy, high. So these antennas work pretty good, pretty popular for the HF bands, and they work very well. Again, you got one antenna that operates over multi-bands. Trap dipoles is another one. The lowest frequency of operation of an antenna acts like a regular dipole. It can be shortened by the inductance of the trap. Yagis can also use traps to work on several bands. 3-element tri-band Yagi with traps and the elements works well 20, 15, and 10. So sort of like what we just looked on the previous chart. That was a Yagi with traps in it. Some drawbacks with traps, because it works on multiple bands, it radiates harmonics and spurious signals also. And so you got to make sure that you've got your transmitter tuned right, and to watch your spurious signals. Traps losses reduce the efficiency of the antenna. They are coil, and they will absorb some of your energy. And they don't radiate as well as a full-size antenna, but it's a great compromise. Okay, what is the characteristics of a random wire HF antenna connected directly to the transmitter? Let's see. It may carry significant RF current. That's what you got to be careful for. You got to look out for, because you can have high SWR on the thing, and got to be careful. In free space, how does the gain of 3-element horizontally polarized Yagi antennas vertically spaced a half wavelength apart typically compared to the gain of a single element? So as we talked about, if you can stack 2 of them vertically, you get about a 3 dB gain, should be V. Yep. What's the primary function of antenna traps? And it's to enable multiband operation. What is an advantage of vertical stacking of horizontal polarized Yagi antennas? Quick selection, simultaneous. It narrows the main lobe in elevation. That's correct. Which of the following is an advantage of a log periodic and antenna? It has wide bandwidth bands. Okay. Which of the following describes a log periodic antenna? Let's see, element spacing vary logarithmically along the boom. That's correct. Gain varies. Sorry, so it had to be A. Okay, the element spacing is logarithmically related. What is the primary use of a beverage antenna? Directional receiving antenna for HF bands. I think that's the right answer. Remember, that's the one that's got a resistor in it, and it's not good for transmitting, but it's great for receiving, and it has some directional to it. Which of the following is a disadvantage of multiband antennas? Must be used, it must be fed. Poor harmonic rejection because the resonance. So if I've got a 2040 multi-dipole and I'm on 20 meters, well, I'm also generating a 40-meter harmonic too. So you got to be careful because that harmonic will be resonant on one of your antennas. Okay, so let's talk about feed lines and characteristic impedance. Bounce feed lines consist of two parallel conductors separated by insulating material in the form of strips or spacers. They have different characteristic impedances that characterize how electromagnetic energy is carried by the feed line. For parallel conductor feed lines, the radius of the conductors and the distance between them is determined by the ZO, which is the impedance. Most common type is window line. Typical impedance for a window line is about 450 ohms, some as low as 400. Most common characteristics of coaxial feed lines, 50 ohms and 75 ohms. Here's an example of some of the different types of feed lines. This is let's see. Here's a 75 ohm twin lead, 450 ohm window line. Coax with different kinds of dielectric materials, different kinds of shielding. A lot of different types of coax shielding is available and insulating materials. And so you have to pick the coax. If you're using coax, you want to get the impedance that you want, get the jacketing, get the shielding that you want, get the jacketing material that you need. If you're burying it outside, it's going to be in sunlight. A lot of factors to consider when picking out your coax and your feed lines. So, right. So let's talk about forward and reflected power and SWR. Feed line transfers all of its power to the antenna when the antenna and feed line are matched. If the impedances don't match, some of that power is reflected by the antenna back towards the transmitter. So we have forward power, it's power traveling down towards the antenna, and reflected power that's reflected back. Power in a feed line is reflected at any point at which the impedance of the feed line changes. So that can not necessarily be at the antenna, but could be at the connector, or you've got an interface coming out of your shack to the outside, a patch panel. Whenever that feed line is interrupted or changes, the impedance can change through that, and you can get a reflection there. SWR, the waves carrying forward power and reflected power from stationary patterns inside the feed line. It's called SWR. This is called standing waves. The ratio of the peak voltage in the standing wave to the minimum voltage is called the standing wave ratio. Standing wave ratio measures how well the antenna feed line and impedances are matched. 1-to-1 is a perfect match. None of the power is reflected. SWR of infinity indicates that all the power was reflected. And SWR is always greater than 1-to-1. For example, you always say 3-to-1. You won't say 1-to-3. 1-to-1's perfect, so there's never a perfect system. So always going to be a little greater than 1-to-1. So how do you calculate SWR? SWR is equal to the ratio of the higher of antenna feed point impedance or feed line characteristic impedance to the lower. So example, what is the SWR in a 50 ohm feed line connected to a 200 ohm load? Well, that would be 200 divided by 50 equal to 4. So that'd be 4 to 1. What's the SWR in a 50 ohm feed line connected to a 10 ohm load? 50 divided by 10, 5 to 1. So remember, it's going to be the ratio of the higher one to the lower one, right? So you're not going to get a number less than 1, okay? SWR can be measured anywhere along the feed line. However, it's most commonly measured at the connection to the transmitter. SWR is measured by an SWR meter, also called a bridge. Transmitting equipment is designed to work at full power with an SWR at the input impedance feed line of about 2 to 1 or lower. Antennas that are much too short or too long will not work well and will have extreme feed point impedance, causing high SWR. Matching feed line and the load, the antenna impedances, eliminate standing waves from reflected power and maximize power delivered to the load. But not always practical. The impedance matching is more often done at the transmitter end of the feed line. Devices used to reduce SWR are called impedance matchers, transmatch, antenna coupler, and antenna tuner. Tuners do not tune the antenna at the amplifier thinks it's got a good match out there. So in other words, an antenna tuner increases the power transfer from the transmitter to the feed line. So if you've got a bad antenna, still a bad antenna. All right. So impedance matching, these are devices constructed from inductors and capacitors that are adjusted by the operator. A T circuit can match a wide variety of impedances at the feed line connection to 50 ohms that matches transmitter output impedance. It's important to remember that the SWR in the feed line between the impedance matching device and the antenna does not change. The device just changes the load going to the transmitter. SWR in the feed line stays the same, okay? So if you've got high SWR with your tuner, you still got high SWR on the other side of the tuner, okay? But your transmitter is going to transfer as much power as it can to the load. So a T network usually consists of 2 capacitors and an inductor. And then there's let's see, the pi network. Okay, so installed at the transmitter end of the feed line, a T network is designed to be used with unbalanced coaxial feed lines. This circuit uses 2 variable capacitors and 1 variable inductor. To use balanced feed lines such as window line, the output of a T network can be inductively coupled to the output so that neither of the feed line conductors is connected to ground. Now, feed line losses. Feed line dissipates a lot of energy. It dissipates a little of the energy that's carried as heat, called attenuation or loss. Loss in the feed line is measured in dBs per unit of length, usually specified as dB per 100 feet. The loss increases with frequency for all types of feed lines. The smaller the cable diameter, the higher the loss. Increasing SWR in a feed line also increases the total loss. The higher the feed line loss, the lower the measured SWR will be at the input to the line. A lot of people don't realize how much loss they have in their coax feed system. If you've got, like I think we had in our earlier talking about dB, a 1 dB loss is you're going to lose 20% of your power. So if you had 100 watts with the 1 dB loss in your cable, putting 80 watts through the antenna, and that other 20 watts is dissipated as heat in the coax feed line. Okay. So what's the purpose of an antenna tuner? Reduces SWR to the feed line, reduces SWR dissipation, increases power transfer from the transmitter to the feed line. It's going to be C. You may want to think an antenna tuner, a lot of people say it reduces the SWR. Well, no, it doesn't. The antenna and the SWR on the other side of the antenna tuner, the SWR is still whatever it was before, so it just makes the antenna, it makes your antenna, allows the antenna to transfer as much power as it can to the feed line itself. Which of the following factors determines the characteristic impedance of a parallel conductor feed line? Let's see, the distance between them. Be A, distance between the centers of the conductors and the radius of the conductors themselves. What is the relationship between high SWR and transmission line loss? Let's see. Yep, high SWR increases loss in a lossy transmission line. What is the nominal characteristic impedance of window line, transmission line? It's about 450 ohms. What causes reflected power at an antenna's feed point? That'd be a difference in the feed point line impedance, the antenna feed point line antenna, and antenna feed point impedance. So it's a mismatch in impedance. How does the attenuation of coaxial cable change with increasing frequency? Okay, so the higher the frequency, the more loss you're going to have. So the antenna increases, so it would be B. And what units is RF feed line loss usually expressed? It's usually in dB per 100 feet, D. What must be done to prevent standing waves on a feed line connected to an antenna? Not A, odd number, not B, C. D. Antenna feed point impedance must be matched to the characteristic impedance of the feed line. If the SWR on an antenna feed line is 5:1 and a matching network at the transmitter end of the feed line is adjusted to present an SWR 1:1 to the transmitter, what is the resulting SWR of the feed line? And it would be 5:1. So B. What standing wave ratio results from connecting a 50 ohm feed line to a 200 ohm resistive load? So it's going to be 200 divided by 50, should be 4, be 4:1. What standing wave ratio results from 50 ohm feed line to a 10 ohm resistive load? In this case, it'll be 50 divided by 10, 5:1. All right, now we're going to talk about the ionosphere, the sun, and scatter modes. So the ionosphere. It's what's called, it's the upper reaches of the atmosphere. It gets thinner with distance. It begins about 30 miles above the Earth. Its remaining gas is thin. It's enough for ionization to occur. The region of the atmosphere becomes a very weak conductor. And you can see here that it's actually 3 layers. There's a D layer closest to the Earth, about 30 miles up. The E layer, the F1, and the F2. The F1 and the F2 combine at night, so it's just one F region at night. And the D and E layer disappear at night. Okay, so it's related to the sun. All right, the D layer, 30 to 60 miles, is only present when illuminated by the sun. It disappears at night because ions and free electrons are close enough together to recombine quickly when no UV is present, returning it to a neutral condition. At night, the D and E regions disappear, and the F1 and F2 regions combine to form a single F region. Okay? So again, the ionosphere consists of several regions of ionized particles, different heights above the Earth. The E layer, 60 to 70 miles above the Earth, acts similar to the D layer. It's higher and less dense than the D region, and it enables it to last a little bit longer after sunset. The F layer, 100 to 300 miles above, is the least dense of the 3 layers, and it remains partially ionized at night. During the day, the F1 region splits into F1 and F2. During at the height of the F region varies quite a bit with local time, season, latitude, and solar activity. So it changes based on those things. At any particular location, the stronger the illumination from the sun, the higher the F2 layer will be. So its maximum height is reached at noon when the sun is overhead. And the ionosphere refracts radio waves. It's a weak conductor. Refraction amount depends on the amount of ionization and wave frequency. The higher the ionization, the more the refraction. The lower the frequency, the more the refraction. So HF signals, relatively good refraction, are reflected back to the Earth's surface. VHF and UHF signals essentially have no refraction. So remember, frequency is related to what gets refracted, okay? VHF, okay, so each reflection is called a hop, and it allows signals to be reached hundreds or thousands of miles away. It's called skywave propagation via the ionosphere, so it's called skip. So skywave propagation via the ionosphere is called skip. The E layer acts similar to the D layer. Oops, sorry about that. Went to my next chart. The higher the region from which the reflection takes place, the longer the hop. Waves reflected from F2 layer travel at 2,500 miles before returning to the ground. Hops from the E layer are shorter, about 1,200 miles. And some combinations of frequency and ionization level result in weak bending. The wave must leave the Earth's surface at a low enough angle for the bending of the wave to be sent back. Highest takeoff angle at which a wave can be returned to the Earth is called the critical angle. Critical angle depends on ionospheric conditions and frequency. Radio waves are reflected and bent in the ionosphere, so they return to the Earth far from the transmitting station. Without refraction in the ionosphere, radio waves would pass directly into space. So I've got a station over here. It's transmitting, hits the ionosphere at the correct angle, and reflected back to Earth, and a station on the other side of the Earth can hear them. If there's a critical angle, because we'll talk about the critical angle over here. Waves that leave the transmitting antenna above the critical angle are refracted in the ionosphere, but not bent to return to the Earth. Waves at and below the critical angle will return to Earth. The lowest angle waves that return to the Earth at the greatest distance, which is why low angles of radiation are often best for DX stations. So depending on how your signal is, the angle at which it takes off from your station depends on does it get reflected back or not. So, and this is called the critical angle here. The critical angle, the critical frequency is the highest frequency at which wave transmitted straight up will return to Earth. Okay. Absorption, the enemy of propagation is absorption. In D and E regions, waves passing through the denser gases are partially absorbed. The D region is not very good at refraction. In HF bands below 10 megahertz, AM broadcast bands, and at lower frequencies, the D region completely absorbs radio waves during the day, preventing those waves from returning to Earth. Absorption increases in daytime and when solar UV is more intense. When is the best time to transmit on HF below 10 megahertz? It's going to be at night. And AM radio stations, that's why they can run the high power during the day. And when the sun goes down, they have to reduce their power because during the day, all their energy is getting absorbed. So it's not going other than locally. But at night, it would bounce off the F layer and would be a big problem. Noise is another enemy of propagation. It covers up weak signals. Stronger at frequencies below VHF. Lower you go in frequency, the stronger the noise or static. It varies seasonally, most noticeably on lower frequency HS bands in the summer when atmospheric noise is the strongest. I know around here in the afternoons, a lot of thunderstorms around the area across the state and staticky. Long path and short path. When ionosphere along short path does not support propagation, sometimes long path will. Occasionally, propagation over long and short paths will be supported at the same time. Unless the paths are almost equal, there will be an echo or delayed signal arrives a fraction of a second later. in my experience, I've done this a couple of times. I've heard my signal go short and long path, and there is a little echo delay. It's a cool thing that happens, and you get all excited about it, but it's pretty cool. It's an amazing phenomenon. Around the world propagation, you can hear your own signal coming all the way around your location about 1/7 of a second later. So when conditions are right, it's a pretty cool thing. And this sketch shows the Earth has both great circle paths drawn between the two stations. So here I've got this is your station, and you transmit, and it goes all the way around the Earth and comes to that station. Or short path is here. This is long path, and this would be short path this way. And like I said, sometimes I can hear you can hear your signal come all the way back around. Kind of cool. Okay, how is a directional antenna pointed when making a long path contact with another station? It would be 180 degrees from the station's short path, C. Like if I'm trying to go here to Texas, I'd point towards the, I guess towards the west. If I was trying to, that's for short path. For long paths, I'd point towards the east, see if I can come all the way back around. What is a characteristic of skywave signals arriving at your location by both short path and long path? Let's see, periodic feeling, a slight echo might be heard, D. What is the approximate maximum distance along the Earth's surface normally covered on one hop using the F2 layer? It's about 2,500 miles, C. What is the approximate length distance of the Earth's surface normally for one hop using the E region? It's about 1,200, B. What ionospheric region is closest to the Earth's surface? That would be the D region, A. What is meant by the term critical frequency at a given incident angle? Highest frequency which is reflected back to Earth. That is the answer, A. Why is skip propagation via the F2 region longer than via the other ionospheric regions? Densest, highest, because it's the highest, C. It's the F2 layer is the highest layer that we have. It's the furthest away. So what does the term critical angle mean as applied to radio wave propagation? Path. It would be D, the highest takeoff angle that will return a radio wave to Earth under specific ionospheric conditions. There are websites you can go to during the day that give you critical angle and frequency and changes, of course, as the sun changes. As you know, so there are places you can go look at the propagation. Why is the long distance communication on 40, 60, 80, and 160 meters more difficult during the day? That's because it gets absorbed by the D region, C. Okay. Which ionospheric region is the most absorbent of signal levels below 10 megahertz during daylight hours? That would be the D region. Okay, sunspots and sun cycle. Let's talk about the sun. Ionosphere is dependent on solar UV to separate electrons from atoms. Much of the variation in UV radiation is due to sunspot activity. One complete sunspot cycle lasts about 11 years. When more sunspots are observed, more UV is being generated, creating more intense ionization, improving propagation on higher frequency bands above 10 megahertz and even into the lower VHF region. Here's a graph that shows the sunspot cycles over time, and you can see it's about an 11-year cycle. We've just come off, I guess, our peak cycle, and it's been fun. In mid-2023, when this book was published, cycle 25 was heating up, and propagation on 10 meters and other bands was increasing. Yep. At peak cycle, there may be sufficient solar UV to cause higher frequency bands, 10 meters, for example, to stay open for long distances during contacts at night. High ionization negatively impacts low frequency bands, 80 to 60 meters, because it increases absorption. When solar activity is low, lower HF bands have good propagation, and higher HF bands above 20 megahertz, 15 meters and up, are often closed. One band that seems to do well at all times in sunspot cycles is 20 meters. It's 14 megahertz. It supports daytime communications worldwide nearly every day. And that's true. 20 meters, you can almost always find something going on 20 meters. Seems to be the sweet spot. And here's a chart showing the propagation on the different bands. What happens during the day, what happens during nighttime. So during the bands, I mean during the day, the low bands are fairly quiet. You can do regional communications. In the state of Alabama, we can talk regionally. When we're doing our areas activities during the day, we can usually communicate. So based on the time of day and the band you're on, and once you get your general license and start getting to the operate on the HF band, you're going to learn all these things here. You're going to experience them. You're going to become an expert on propagation, when to communicate, where, what bands are good. It's a whole lot of fun. Okay. Sunspots also seem to move across the sun's surface because the sun rotates once every 28 days. That is why propagation conditions, good and bad, on the HF bands often repeat themselves in a 28-day cycle as sunspots rotate back into view from Earth. Measuring the solar activity, you can measure the number of sunspots. There's a thing called the solar flux index. It describes the amount of 2,800 megahertz radio energy. High levels indicate high solar activity and better HF propagation above 10 megahertz. The thing called the K index has a value from 0 to 9. It represents the short-term stability of the Earth's magnetic or geomagnetic field. Higher values indicate geomagnetic field is disturbed, which disrupts HF. An A index gives a good picture of long-term geomagnetic field stability, and it ranges from 0, stable, to 400, greatly disturbed. It's calculated from the K index. And there are sites you can go to that have this information real time. And so the solar activity is so important to propagation and communication that is monitored constantly. And like I said, you can go to certain websites and get these values and the information on the sun. Okay, so how does a higher sunspot number affect HF propagation? And the answer is A. Higher sunspot numbers generally indicate a greater probability of good propagation at higher frequencies. Which of the following are least reliable for long distance communications during periods of lower solar activity? That would be 15 meters, 12, and 10. That's when we've got low solar activity, higher bands. What is the solar flux index? It is a measure of the solar radiation at the 10.17 centimeter wavelength band. At what point is the solar cycle does the 20-meter band usually support worldwide propagation during daylight hours? Usually it's all the time. D. It's really not affected. I mean, it's affected, but it usually does fairly well. 20 meters is a place you can usually go to and find some activity, no matter what time of day. What causes HF propagation conditions to vary periodically in a 26 to 28 day cycle? And that would be the rotation of the sun's surface layers around its axis, C. What does the K index measure? It measures the short-term stability of the Earth's magnetic field. What does the A index measure? And it's the long-term stability of the Earth's geomagnetic field. Which of the following is typical of the lower HF frequencies during the summer? Let's see. High levels of atmospheric noise and static. I think that is correct. Okay, so let's talk about propagation. There's some terms. There's a maximum usable frequency called MUF. It's the highest frequency at which propagation exists between 2 points. The lowest usable frequency, LUF, waves below the LUF will be completely absorbed by the ionosphere. MUF and LUF depend on specific data between 2 points, locations and distance apart. It varies with the time of day, season, amount of solar radiation, and ionospheric stability. Operating near the maximum usable frequency often gives excellent results. Absorption is lowest, just below it. One way to check actual conditions is to listen for propagation beacons. Some provide real-time propagation information. Many stations between 28.19 and 28.225 megahertz that are excellent sources of information about 10-meter propagation. To make contact with the distant station, you will have to use a frequency between LUF and MUF so the wave is bent back toward the Earth but isn't absorbed. If the MUF drops below the LUF, then no propagation exists between those 2 points via ordinary skywave. And there's on the web you can go find maps of the world that show the MUF and the LUF, and it's got what the propagation is between different points on the Earth and the bands that are open, and a lot of good information out there. Okay, let's talk about solar disturbances. Approximately 8 minutes after a solar flare occurs on the sun, the ultraviolet and X-ray radiation released by the flare reaches the Earth. This radiation causes increased ionization and radio wave absorption in the D region. A solar flare, which is a large eruption of energy in solar material when magnetic field disruptions occur on the surface of a solar flare, is a large eruption of energy in solar material when magnetic field disruptions occur on the surface of the sun. A coronal hole, which is a weak area in the sun's corona, the outer layer, through which plasma, ionized gas, and charged particles escape the sun's magnetic field and streams away into space at high velocities. A coronal mass ejection, CME, is an ejection of large amounts of material from the corona. And all of these disrupt HF propagation. Some sudden ionospheric disturbances. UV and X-ray radiation from a solar flare travels at the speed of light to impact the ionosphere about 8 minutes later. When radiation hits the ionosphere, the level of ionization increases rapidly, particularly in the D region. This increases absorption dramatically, causing a sudden ionospheric disturbance, also known as a radio blackout. Lower bands are more strongly affected, but communication may still be possible on a higher band. Sudden ionospheric disturbances affect only the sunlit side of the Earth. The dark side communications may be relatively unaffected. Geomagnetic disturbances. This is the interaction between solar wind and geomagnetic field, which creates a region of space called the magnetosphere. Charged particles from coronal holes and coronal mass ejections travel considerably slower and take longer to reach the Earth, about 15 to 40 hours. These particles deposit their energy into Earth's geomagnetic field and increase ionization in the E region, causing auroral displays and creating a geomagnetic storm, which affects higher HF bands first. Long-distance paths that traverse high latitudes, particularly those that pass near the magnetic poles, may be completely wiped out for days, for hours, or days. And these can create auroras that reflect radio waves above 20 megahertz. Auroral propagation is strongest on 6 meters and 2 meters, modulating the signals with a hiss or a buzz. So sometimes you can actually hear it on the signals. There's a modulation that happens. Kind of a cool effect. So here's some questions. What effect does a sudden ionospheric disturbance have on the daytime ionospheric propagation? B, it disrupts signals on low frequencies more than those on higher frequencies. Approximately how long does it take for increased ultraviolet and X-ray radiation from solar flares to affect radio propagation on Earth? About 8 minutes. And what is a geomagnetic storm? It's a temporary disturbance in the Earth's geomagnetic field, that BT. How can a geomagnetic storm affect HF propagation? It degrades high latitude HF propagation. How can geomagnetic activity benefit radio communications? By creating auroras that can reflect VHF signals. How long does it take a coronal mass ejection to affect radio propagation on Earth? Usually it's about 14 hours to several days. It just depends. How is long distance radio communication usually affected by the charged particles that reach Earth from solar coronal holes? HF communication is disturbed. What factors affect the MUF? Just the maximum usable frequency. Path distance, time of day, solar radiation, all of those affect what the maximum usable frequency is. Which frequency will have the least attenuation for long distance skip propagation? That would be just below the maximum usable frequency. Which of the following is a way to determine current propagation on a desired band from your station? Use a network of automated receiving stations on the internet to see where your transmissions are and being received, because it's different all over the world, given at a given time. So check a network and see what the receiving stations are showing at a particular given time. How does the ionosphere affect radio waves with frequencies below the MUF and above the LUF? Yeah, they are refracted back to Earth. What usually happens to radio waves with frequencies below the LUF? They are attenuated before reaching the destination. So not going to get through. What does LUF stand for? It's the lowest usable frequency for communication between two specific points. Okay. What does MUF stand for? It's the maximum usable frequency between 2 points. All right. And what happens to HF propagation when the LUF exceeds the MUF? Propagation is not possible over that path. That's correct. All right, let's talk about some scatter modes. There's some terms called backscatter. That's reflections from features on the Earth's surface. Waves can also be scattered from within the ionosphere, allowing signals to be heard from stations too distant to be heard by ground wave and on frequencies too high for short hop skywave propagation. Scatter and backscatter help fill in the skip zone where signals would otherwise not be heard. Signals received via HF scatter are usually weaker than those received by normal skywave propagation. Reflection is not very efficient and tends to spread out the signal. Such signals sound distorted, resulting in fluttering or wavering. On striking the ground after ionosphere reflection, radio waves may be reflected back towards the transmitting station. Backscatter consists of signals reflected by the ground back into the skip zone. Backscatter supports communication between stations that would otherwise be in each other's skip zone. So I've got a signal. I've got a station transmitting here, and I've got another receiving station. He's out of my skip zone, but because of some backscatter, some of that is actually received by this particular station. So the skip distance, he's too far. He's out of my skip zone, but scattered signals from the ionosphere, he can sometimes hear me. And usually those are weak signals and they're fluttery, but that's a way I can communicate. Near vertical incident skywave, NVIS. We just talked about what's an NVIS, how we can build an NVIS and NVIS antenna. For a signal below the critical frequency, the ionosphere reflects waves arriving at the angle, even vertical, always above 5 megahertz up to 40 meters. NVIS is for a signal below the critical frequency. When it is radiated vertically, the reflected scatters the signal back to Earth through the region of up to 200 to 300 miles. To make use of NVIS, horizontally polarized dipoles are placed low to the ground so that the radiation pattern is almost omnidirectional and concentrated at high elevation angles. Near vertical incident skywave or NVIS communication relies on signals below the critical frequency transmitted at high vertical angles. The signals are reflected by the ionosphere back to Earth in the region around the transmitter. So here's an example. Got a transmitting station here. I've got a guy on the other side of this mountain. I can't talk to him directly, but I can bounce the signal off the ionosphere and get to him. And you're using the F layer to do this these reflections. Okay, what's the effect of HF scatter? What's the characteristic of HF scatter? They have a fluttery sound, usually weaker signals. What makes HF scatter signals often sound distorted? It's because they're it's scattered into the zip zone along several paths. Okay. Why are HF scatter signals in the skip zone usually weak? It's because only a small part of the signal is scattered back into the skip zone. What type of propagation allows signals to be heard in the transmitting station skip zone? That would be scatter. What is a near vertical incident skywave propagation? And that is short distance MF or HF propagation using high elevation angles. Okay, our next section, we're going to talk about electrical safety, RF exposure, and outdoor safety. So first of all, talking about electrical safety, preventing electrical shock. Always have a master on-off switch for station and workbench, clearly labeled and somewhat away from the equipment. Don't put yourself in a position to be shocked. When working inside equipment, remove, insulate, or secure loose wires and cables, and use a ground stick to remove charge from capacitors. So you might say, what's a ground stick? Well, yeah, here we go. Here's a ground stick. Ground stick is a ground stick. It's touched to all circuitry inside an enclosure to ensure that no high voltage is present. The alligator clip is attached to an electrical ground, and the eye bolt is put on a contact with the circuit. So you've got an insulating piece of PVC pipe, and this allows you to touch certain components and discharge them to the potential of the ground itself. So what's the effects of electrical current through the human body on an average person? Well, below a milliamp, generally you can't perceive it. 1 milliamp, faint tingle. 5 milliamps, slight shock. 6 to 25 milliamps, painful for women. 9 to 30, painful for men. Just the freezing, you can't let, that's in the let go range. 50 to 150 milliamps, very painful. And this is if you had contact, inside the body. Your skin is a resistance, so that helps. But can be very painful. So it doesn't take much current to cause problems with the human body. Soldering safety. So primarily, solder is primarily lead-based. Tin is added to lower the melting point. Lead is a known toxin. Always solder in a well-ventilated area. Rosin, flux, smoke is likely not good for you in high doses. Use a well-ventilated area if you can. When finished, wash your hands to remove solder or flux residue. As of 2006, environmental regulations were passed for solder to eventually be lead-free. Leaded solder is still available. Lead-free solder melts at significantly higher temperatures than traditional 60-40 solder. Greater risk of damage to heat-sensitive components because you've got to run at a little higher temperature. So which of the following is a danger for lead tin solder? Lead tin can contaminate food in your hands. Carefully, carefully, wash your hands after you've handled lead tin solder. Okay, wiring practices. National Electrical Code Handbook contains the details for handling AC wiring in the home and the station. Use your local building codes to ensure that home is properly wired to meet special local conditions. Use standard wire color conventions. Hot, which is red or black insulation, is connected to the brass terminal or screw. Neutral, which is white insulation, is connected to the silver terminal or screw. And green, your ground is your green insulation or bare wire is connected to the green or bare terminal screw. So those are the standard wiring, AC wiring conventions used in your home. Don't run antenna feed lines, over power lines, or service drops from a transformer to the house. Okay, here's some standard wiring conventions. Standard wiring for outlets, 100 120 and 200 volt AC plugs and receptacles. It's critically important to follow the correct wiring techniques for AC wiring. The white wire is neutral, green wire is ground, and the red or black wire is the hot lead. Note that 240 volt circuits may have 2 hot wires and a ground. So be careful when you wiring things or hooking things up. Observe the wire colors and the correct connections. House AC wiring, most common sizes are number 12 gauge for 20 amp circuits and 14 gauge for 15 amp circuits. Use fuse or circuit breakers for the hot conductor for 120 volt circuits on both hot, and use them on both for the hot conductors on a 240 volt circuit, which uses the 3 or 4 wires. All right, here's some current capacity ratings for some common wire sizes. The rating of a wire to carry current is called its ampacity. When you are finished wiring the job, verify that you have the correct connections by using an AC circuit tester. So make sure you follow the right proper wiring sizes for the right conductors. All right. Fuses and circuit breakers are used to interrupt excessive current flow. Fuses do so by melting a short length of metal. Circuit breakers act like a fuse but trip when current overloads occur. Always use properly sized fuses and circuit breakers when installing fuses or circuit breakers in an AC circuit. Be sure to replace them only with the correct ones, never in the correct lines, never in the neutral or ground lines. Be sure there's a fuse or circuit breaker in the hot conductor for 120 volt circuits and both conductors for a 240 volt circuit. Ground fault interrupter circuit breakers are used in AC power circuits to prevent electrical shock. It trips if unbalance is sensed in currents carried by the hot and neutral conductors. Its sensitivity is just a few milliamps of imbalance between the hot and neutral, well below the threshold for electrical injury. Safety interlocks. This is a switch that prevents dangerous voltages or intense RF from being present when a cabinet or enclosure is opened. You'll see these a lot if you have a high power amplifier, especially tube amplifiers. When you take the top off, there's usually a switch that disables all the voltages. So if you're working on it and if you've got to bypass that, be real careful. All right, several types. Physically disconnect high voltage RF when activated. Those are the switches I was just talking about. Usually take the chassis apart. There's usually a little rocker switch or some kind of switch in there that senses that. Shorts or ground high voltage circuits when activated, possibly blowing a circuit breaker or fuse in the power supplies. Which wire or wires in a 4-conductor 240 volt AC circuit should be attached to fuses or circuit breakers? Okay, only the hot wires. A, you should not fuse the ground or circuit, or you should not fuse the ground wires. According to the Natural Electric Safety Code, what is the minimum wire size that may be used safely for a 20 amp circuit? That would be the 12 gauge wire. What size of fuse or circuit breaker would be appropriate to use for a circuit that uses a 14 gauge wire? That would be the 15 amp circuit breaker. Which of the following conditions may cause a ground fault circuit interrupter to disconnect AC power? Current flowing in one or more of the hot wires to the neutral, or the hot wires to ground, over voltage of the wires. It would be current flowing from one or more of the hot wires directly to the ground. B. Which of the following is covered by the National Electric Code? That would be the electrical safety of the station. What is the purpose of a power supply interlock? Let's see, it would be to ensure dangerous voltage are removed from the cabinet when it's open. That would be C. Okay, some generator safety. Fueling and ventilation problems cause more injuries associated with generators than from any other cause. Install generators outdoors. Use them outdoors. Carbon monoxide in exhaust can quickly build up to toxic levels. When using generators, regularly install carbon monoxide detector alarms in living and working areas. Generator output connected directly to the home's wiring system must have the ability to disconnect power service from utility lines. Generators should always be shut off when refueling to avoid igniting fumes or splashing liquids from the spark plug. A fire extinguisher should be kept near the generator and separated from the fuel. Here's some practice questions. Which of the following is true of an emergency generator installation? Generator should be operating well operated, must be insulated from ground. It would be A, should be operated in a well-ventilated area. Lighting. Lightning. Goals of lightning protection. You should provide fire prevention for your home. It reduces or prevents electrical damage to your equipment. Use metal entry panels where signal and control cables enter the house. Panels should be grounded nearby with a heavy metal strap. Ground rod must be bonded to the AC service entry ground rod outside the building with a heavy conductor. And lighting arresters should be installed at the entry panel where the feed line enters. Grounding wires and straps should be as short and direct as possible. Do not use solder or to make ground connections. Solder joints could melt if hit by lightning size current. Use medical clamps, brazing, or welding. So, never use a solder connection never use solder to make ground connections where you can have lightning come in. All towers, masts, and antennas should be grounded. Why should solder joints not be used in lightning protections? Because a solder lightning will likely be destroyed by the heat of lightning. A. Where should the station's lightning protection ground system be located? It should be outside the building, of course. Which of the following is required for lightning protection ground rods? Lightning rod must be connected. D, they all must be bonded together with all other grounds. Where should lightning arresters be located? Where it enters the building. Okay, RF exposure. At high power levels, for some frequencies, the amount of energy that the body absorbs can be a problem. The maximum permissible exposure, MPE, is maximum intensity is the maximum intensity of RF radiation to which a human being may be exposed. Factors to consider when estimating MPE, that is transmitter power level or density, frequency, average exposure time, and duty cycle of the transmission. Power density and frequency are primary ones. Those are things that you should think about. How much power you're putting out, what's your frequency, what's your exposure time, and the duty cycle. Stations with a time average transmission of more than 1 milliwatt are subject to the FCC's RF exposure rules. If your station exceeds the exemption criteria, you will need to evaluate it and according to the FCC OET Bulletin 65. So what does that mean? So talk about that in a minute. Power density is heating from exposure to RF signals caused by the body's tissue absorption of RF energy. It's measured in milliwatts per centimeter squared. RF field strengths can also be measured in volts per meter and amps per meter, or milliwatts centimeter squared is the most useful for amateur requirements. Power density is highest near antennas and in the directions in which antennas have the highest gain. Decreasing transmitter power and increasing distance from the antenna lowers power density, and vice versa. Absorption and limits. SAR, which is specific absorption rate. This is the rate at which energy is absorbed from the power to which the body is exposed. It's the best measure of RF exposure, but it's difficult to measure. SAR varies with frequency, power density, average amount of exposure, and duty of cycle of transmission. SAR depends on frequency and size of the body or body part affected. Highest where the body or body parts are naturally resonant. Safe levels of SAR based on demonstrated hazards have been established by the FCC in the form of maximum permissible exposure limits, or the MPE levels. Maximum permissible exposure, MPE limits, vary with frequency because the body responds differently to energy at different frequencies. The controlled and uncontrolled limits refer to the environment in which people are exposed to the RF energy. These take into account the variation of the body's sensitivities to RF energy at different frequencies. So you can see here that based on the frequency, the power density levels in a controlled and uncontrolled environment at different frequencies. So in this particular case, this is where the body is most sensitive to RF radiation. The limits of occupational controlled exposure, these are you got frequency range, the power density, controlled environment, and the uncontrolled environment ranges. Controlled exposures limits supplies to controlled exposure limits apply to individuals trained in RF exposure, such as licensed amateurs. An uncontrolled environment is the general public, and their levels are just a different level, are just a little higher. The uncontrolled exposure limits apply to individuals not trained in RF exposure, such as the general public. And you'll notice here, so these are the frequency ranges and their exposure levels and the average time. You're required to do an exposure analysis for your station. There's an RF calculator at the ARRL that allows you to put in some of these things here, such as transmitting frequency, antenna gain, and it will calculate the safe distance based on the exposure levels that you need to maintain. Okay. The things that control the things that control duty cycle in the uncontrolled environment are exposure to RF energy, which is averaged over fixed time intervals. Time averaging evaluates total RF exposure over a fixed time interval. Two types of averaging periods are controlled and uncontrolled. The controlled is where you're aware of your exposure and are expected to take reasonable steps to minimize. In controlled environment examples, transmitting facilities near antennas. Uncontrolled environments are like general public access. People in an uncontrolled environment are not aware of their exposure, but are much likely to receive continuous exposure.
Sure.
Duty cycle is a ratio of the time the transmitter is on to the total time during the exposure. Maximum is 100%. Same as duty factor, but duty factor is expressed as a fraction. A lower transmission duty cycle permits greater short-term exposure levels for a given average exposure. The less time the transmitter is on, the lower the average exposure, permitting greater short-term exposure levels for a given average exposure. Along with operational duty cycle, the different modes themselves have different emission duty cycles. Operating duty factors of modes commonly used by amateurs. For most amateurs, operating, listening, and transmitting time are about the same. So duty cycle is rarely higher than 50%. Calculating the average duty cycle power, a station is using single sideband without speech processing, transmitting and listening for equal amounts of time, and with transmitter power of 150 watts, calculating the average output power. Average duty power cycle is equal to the transmitted power times the emission duty cycle times the operating duty cycle. So if you've got a transmitting power of 150 watts and you've got a duty cycle for about 20% processing, operating 50% of the time, then your average duty cycle power would be 150 watts times 20 times 50%, about 15 watts. Let's see here. Let's back up and do a section again here. You guys are talking. I know you guys are talking, but it's kind of affecting me a little bit.
Oh, I'm sorry.
No, that's okay. I just want to redo a section.
Which one?
Talking about we're going to go back to figure. I mean, you guys. Let's go back, starting with RF exposure, section 9.2, slide 32.
Okay.
Okay, so I'm going to start here, and I know you guys talk, but it was sort of distracted me a little bit, and I was
Okay.
not.
Oh, my apologies.
Yeah, that's okay.
Yeah.
I just figured, let me go back and do that section again.
Okay. Is this the last section?
Yeah, this is the last thing.
Okay.
We're 32 of 64. We have 32 slides left, and we're done.
Okay. Okay.
But I was more reading. I was getting a little. It didn't sound too good what I was doing.
Okay. Okay. Okay.
So
Yeah. Well, let me look at this real quick.
see if you got enough. See if you got enough time.
I should be fine. You got 36 minutes left. So,
Okay, I
yeah.
think I can do that.
Well,
So-
it'll all be on the same file.
Yeah.
So I'll just take
Okay.
this section, cut it
So
out, and use this as
We're going to start RF exposure again.
Okay.
Okay. So you can find this chart and do it again. All right, sorry about that. Just want to make sure it just sounded pretty good. Okay, we're going to talk about RF exposure. This has to do at high power levels for some frequencies, the amount of energy that the body absorbs can be a problem. There's a maximum permissible exposure called MPE, and that's the maximum intensity of RF radiation to which a human being can be exposed. Factors to consider when calculating your MPE are transmit power level or density, the frequency, the average exposure time, and the duty cycle of the transmission, which is power density and frequency are the primary ones here. Stations with a time average transmission of more than 1 milliwatt are subject to the FCC's RF exposure rules. If your station exceeded the exemption criteria, you will need to evaluate it according to the FCC, and it has an OET Bulletin 65. The ARRL has a online calculator where you can go calculate what the RF exposure is or what's the minimum distance someone needs to be from your transmitting antenna. And we're going to talk about there's two environments. We'll talk about power density first. Power density is heating from exposure to RF signals is caused by the body tissues absorbing RF energy. It's measured in watts per milliwatts per centimeter squared. RF field strengths can also be measured in volts per meter or amps per meter, but milliwatts per meter centimeter squared is the most useful for amateur requirements. The power density is highest near your transmitting antennas in the directions of which the antennas have the most gain. Decreasing the transmitting power, the transmitter power, and increasing the distance from the antenna will lower the power density, and vice versa. The absorption in limits, there's a unit called SAR, which is a specific absorption rate. It's the rate at which energy is absorbed from the power from power to which the body is exposed. It's best to measure your RF exposure, but sometimes it's best to measure it, but sometimes it's difficult to go out to actually do it, and it varies with frequency, power density, average amount of exposure, and duty cycle. All those are factors that come into the SAR measurement. It also depends on the frequency and size of the body and the body part affected. It's highest where the body and the body parts are naturally resonant. Safe levels of SAR are based on demonstrated hazards and have been established by the FCC in the form of maximum permissible exposure limits. So they've taken all this to effect and they've come up with the thing called the MPEs. MPE is the maximum permissible exposure, and these limits vary with frequency, and they've come out and characterized the MPE based on frequency and power densities. And this chart here shows that. And there's two levels. There's a controlled environment and an uncontrolled environment. The controlled environment is where is where the people are aware of RF, and usually controlled by can be controlled by access. Let's see. I'm going to do this chart again.
Okay.
Okay. We're doing.
Because the noise.
Yeah, you sort of noise in the distract again. I'm talking. That's okay. Okay, maximum permissible exposure or MP limits vary with frequency because the body responds differently to energy at different frequencies. The controlled and uncontrolled limits refer to the environment in which people are exposed to the RF energy. These take into account the variations in the body's sensitivity to RF energy at different frequencies. The limits for occupational and controlled exposure are shown here. The controlled exposure limits apply to individuals trained in RF exposure, such as licensed amateurs. Uncontrolled exposure limits apply to individuals not trained in RF exposure. So usually that's the general public. Okay. RF exposure of RF energy is averaged over fixed time intervals. Time averaging evaluates that the total RF exposure over a fixed time interval. Two types of averaging periods. There's the controlled and the uncontrolled. In the controlled averaging, you're aware of your exposure and are expected to take reasonable steps to minimize. Controlled environment examples include transmitting facilities near antennas. An uncontrolled environment would be like public access. People are in an uncontrolled environment are not aware of their exposure, but are much less likely to receive continuous exposure. Duty cycle is the ratio of the time the transmitter is on to the total time during exposure. Duty cycle is expressed in a fraction instead of 25%. So a lower transmission duty cycle permits greater short-term exposure levels for a given average exposure, called operational duty cycle. The less time the transmitter is on, the lower the average exposure, permitting greater short-term exposure levels for a given average exposure. So along with the operational duty cycle, the different modes themselves have different emission duty cycles. 20 to 40% duty cycle. If you're doing a single sideband with AFSK or slow scan TV, that's 100% single sideband, excuse me. And voice amplitude, like AM modulation is 50%, 100% AM modulation is 25% duty cycle. FM voice, 100% duty cycle. Digital FM, 100%. So all the digital modes that we use, that we talked about, are 100% duty cycle modes, like JTA. When your transmitter's on, we consider it's 100% duty cycle. Okay. Calculating the average duty cycle, if a station is using single sideband without speech processing, transmitting and listening for equal amounts of time, and when transmitting power of 150 watts, how would we calculate that average power output? So the average duty cycle power is the transmitted power times the emission duty cycle times the operating duty cycle. So in this particular case, we've got 150 watts, where we've got an emission duty cycle for single sideband of about 20%, and our operating duty cycle is 50%. So our average duty cycle power, I got 150 watts, but I'm times 20% of my emission duty cycle times transmitting 50% of the time, I get 15 watts. If you want to, all fixed amateur stations must evaluate their capability to cause RF exposure no matter whether they are using high or low power. Limits vary with frequency and PEP. You're required to perform the evaluation if your power exceeds the level shown for any band. The RF exposure evaluation is limited by 3 different methods. Measuring RF field strength with calibrated meters, using a computer or model to calculate your exposure, or the easiest way is to use the ARRL's online calculator for RF exposure. So what you need to do to use the exposure calculator is what's the power of your antenna, including adjustments for duty cycle and feed line loss. You got to know your antenna gain, your height above ground, and your operating frequency. And when you have those items, you can go use the exposure calculator to figure out what the exposure is around your antenna system. What I've done for my home is I know what antennas I have, I know what operating modes I use, and I go run that calculation through the ARRL calculator. I print those out, and I've got those at my station, so I know how far or how close people can be to my systems. And for my home use, I'm in pretty good shape. I've got a unfenced backyard, but my worst case is like 10 feet from the end, from the antenna, and all my antennas are 10 feet above the ground. So my RF exposure analysis shows them in pretty good shape. Whenever I go do a public service event, if we're out in the public, like a field day, you should go do an exposure analysis of the antennas that you're going to be used. And if you've got an area where the public can get close to your antennas, then you're going to have to use some barriers to mark it off or to keep people away. Okay. So here's some good practices for RF exposure. Locate and move your antennas away from where people can be exposed to excessive RF fields. Locate the antennas away from property lines and place fences around the base of the ground-mounted antennas. Don't point gain antennas where people are likely to be. Use beam antennas to direct RF energy away from the people. When using stealth, attic, or indoor antennas, make sure your MPE limits are not exceeded in your living quarters. VHF and UHF, place mobile antennas on a roof or trunk of a car to maximize shielding of passengers. Use dummy load or dummy antennas when testing a transmitter. And of course, reduce the power and duty cycle of your transmissions. Okay, here's some questions. What's one of the ways that RF exposure can affect human body tissues? It can heat up the body tissue. That's what RF exposure does. You feel it as heat. You'll hear people talk about RF burns. Which of the following is used to determine RF exposure from a transmitting signal? Power density, duty cycle, all of these are correct. All those affect how much your RF exposure. How can you determine that your station complies with FCC RF exposure regulations? You can calculate it using the FCC OET bulletin, computer modeling, using field string. All those are ways in which you can measure your compliance with RF exposure. What does time averaging mean when evaluating RF radiation exposure? It's the average amount of time power is applied by the transmitter, average time, it's the total time. It's the total RF exposure over a certain period. It would be D. What must you do if an evaluation of your station shows that the RF energy radiated by your station exceeds permissible limits for possible human absorption? Take action to prevent exposure to the fields, file an impact FCC, secure written permissions. It would be A. Take action to prevent human exposure in the excessive RF fields. What must you do if your station fails to meet the FCC RF exposure exemption criteria? All right, so what must you do if your station fails to meet the FCC RF exposure criteria? So what you want to do is A, perform an RF exposure evaluation according to those bulletins, okay? What is the effect of modulation duty cycle on RF exposure? The higher the duty cycle creates, the higher the duty cycle permits greater power levels to be transmitted. That makes sense. The more your transmitter's on, the higher the RF exposure is going to be. Which of the following steps must an amateur operator take to ensure compliance with FCC regulations? Let's see, post a copy, it's going to be C. Perform a routine RF exposure evaluation to prevent access to any identified high exposure areas, okay? And what type of instrument can be used to accurately measure RF field strength? Let's see, that'd be B, a calibrated field strength meter with a calibrated antenna. What should be done if evaluation shows that a neighbor might experience more than the allowable RF limit of exposure from the main lobe of a directional antenna? You can change the antenna height gain, use an antenna with a higher front to back. Take precautions to ensure, it would be C. Take precautions to ensure that your antenna cannot be pointed in the direction when they are present. Okay. What precautions should you take if you install an outdoor transmitting antenna? Be C. Make sure the MPE limits are not exceeded in occupied areas. Okay, what stations are subject to FCC rules on RF exposure? That would be D, all stations with a time average transmission of more than 1 milliwatt. Okay, let's talk a little bit about outdoor safety, installing antennas. Make sure you place all antennas and feed lines well clear of power lines. No part of an antenna system should be closer than 10 feet from power lines. When working on roofs, trees, or towers, Helpers should wear appropriate protective gear at all times, run through a safety checklist every time, turn off and unplug all AC equipment, locking circuits out and tagging them if possible. Transmitters should be off and disconnected from feed lines to avoid shock or excessive RF exposure. Belts and harnesses must be within their service life and adequately rated for the weight. Of course, check the weather report and of course, take your time. Here's some practice questions. Which of these choices should be observed when climbing a tower using a safety harness? Confirm that the harness is rated for the weight of the climber and that is within its allowable service life. What should be done before climbing a tower that supports electrically powered devices? You should make sure all circuits that supply power to the tower are locked out and tagged.